This video is likely to be one of the most valuable concepts you can understand: shock tuning via the chassis mounting locations. It applies to all vehicles, RC, full scale, F1, motorcycles, bicycles, anything with a sliding shock and swing arms. Now, this video I call the exact math version. It's not much harder than high school trigonometry, but I know not everyone has the patience or interest in this level of detail. Watch this video once just so you're familiar with the concept. Then there is a simpler version that I call the intuition or feelings version that explains the same principle, but it does it in a more intuitive fashion. In that video, we'll jump straight to the conclusions. I'll give you some simple tricks to remember which mounting locations change the performance in which direction. So look for that if it's more your style. On this channel, we look at the science behind our grown-up toys. Let's check it out. Shock mount chassis locations. Why are there so many shock mount options? I will break it down for you. Let's start with this diagram to begin the discussion. This represents a shock in the 90-degree orientation. Blue lines represent the different possible shock angles. The grid behind is theoretical chassis mount locations, and your suspension arm or axle is down at the bottom. Just to give you a visual, this is the shock angle we are talking about as the shocks might sit on your vehicle. If you're looking at your vehicle from the front or the rear, these concepts also apply to any angle your shock might have in this orientation. Now that we've established the fundamentals, let's get into the good stuff. Changing your shock position on the chassis changes two things: ride height and shock tune. If you are moving your shock mounting location horizontally or vertically, you are changing both your ride height and your shock tuning. So you want to be sure you are moving holes in the desired direction, not just indiscriminately. To adjust your ride height or your axle height, only adjust your shock along the axis of the shock. This won't affect your shock tuning. It will isolate just the axle position. Changing the angle of the shock changes your shock performance characteristics, also known as shock tuning or shock tune. Let's make sure we all start on the same page by understanding this diagram. 90 degrees is not necessarily vertical. Let's be sure to establish 90 degrees. If you have a trailing arm design, 90 degrees would be perpendicular to that trailing arm. If your trailing arm is not horizontal at some angle, then 90 degrees is perpendicular to that trailing arm. Many vehicles have a 4-bar linkage like crawlers and mountain bikes. Ideally, you would want to orient your framework using the center of curvature, but that's not always easy to calculate. So this method will get you close enough. Average the position between the two links and set your 90 degrees based on that. If you have a double wishbone suspension, then you want to look primarily at the link that is driving the shock. But for an exact picture, you kind of need to analyze the whole thing. This will get you close enough to start. Now let's have a quick trigonometry refresher. Let's say that this 90-degree position is called 100%, and the horizontal position is called 0%. So when your shock is aligned on this axis, you've got 100% response at the wheel from your shock. And this represents the different angles that you can lay your shock down all the way to 0%. Now you might think that halfway in the middle at 45 degrees equals 50%. Well, that's not correct. It's actually 71%. Why is that? Thanks to Engineering 101 and vector components, the vertical component of the force pushing against your axle is reduced to 71%, of the shock force, which is in this direction now. Your swing arm is moving vertically, so it only feels this portion of the shock force. It no longer feels the full effect of the shock. And that's calculated by cosine 45, or a squared plus b squared plus c squared also works. Here I made it really simple to see the difference between all the angles, and I will put a link to these images if you want to refer to them later. First, let's talk about axle or ride height. So if you want to raise or lower your rear axle relative to the chassis, you want to move your shock radially, or in this direction only. That way you don't affect the shock tune. You're only affecting the ride height or the axle height. After you're happy with that, don't move the shock any further in this direction. You want to change as few of the variables at a time as possible. Now let's move on to shock tuning. In order to make shock tuning changes, you want to swing the shock through different angles along this arc. Again, keeping the radial position in this direction along the shock axis fixed. This will change only the shock tuning and not change the axle height at the same time. Again, if you're moving left and right, up and down, you're affecting too many variables at the same time. Changing this angle of the shock will affect 4.5 variables, and it changes them all simultaneously, which probably is not the ideal response, but I will show you how to deal with that. The first thing that changes is the spring force, then the damping force, the wheel travel, and also the progression. The progression is an advanced topic that I'll cover in a different video. And last but very least, I give this just an honorable mention. The center of gravity changes, but it's pretty small. Here's a quick snapshot to show you how the spring force changes. It goes from its firmest orientation and gets softer as you lay it down. The same thing happens with your damping force. It's slower when it has the maximum effect, and your oil weight becomes less effective as you lay the shock down, which means the reaction at the wheel is faster. Also, your wheel travel actually goes up as you lay the shock down. When the shock is in the 90-degree position, you've got 1-to-1 travel, and as you lay it down, that travel gets exaggerated and you get more and more travel. The first variable, starting spring force. If your spring rate is 1 Newton per millimeter, your wheel will feel that 100%, or 1-to-1 in the 90-degree position. As you lay the shock down towards 0%, the force felt at the wheel goes down. Now, this might be all you need to know. The shock goes from firmer to softer. We're about to go deeper, so hang tight. Remember the 71% thing? Here's where that comes into play. Notice that the difference from 80 to 90 degrees doesn't make much difference in the spring force. But 50 to 40% change makes a much bigger difference, 77% to 64%. Now, the difference between 77 and 64 is not 13%. It's actually a 17% difference in the percentages. So that's huge. I don't recommend making changes bigger than about 10% at a time. So as you can see, as you lay your shock down further and further, the impact at the wheel becomes greater and greater, which is the important thing to be aware of. Again, up here at 90 to 80, not much difference. It starts to really accelerate as you come down. And when you get all the way down to 20 or 10%, this really can't even be used in real life. Now I've made it even easier by putting together the exact percent change between each of these. It's much easier to read 2%, 5%, 8%. Here's that 17% difference between 50 degrees and 40 degrees. And as you can see, it gets greater and greater. I think looking at the delta is more valuable than looking at the exact percentages. So you want to be careful when you're making these changes so you have an idea how pronounced those changes are. I'm going to introduce something I call parallel tuning options. Now, shock angle is not the only way to change your effective spring force. You can also change the spring response by changing the spring itself to a different rate altogether. Let's say you want a softer spring response, but you don't want to change your shock angle, or vice versa. You have two ways to make your spring response softer. Also, don't confuse spring rate with preload. I'll explain that in another video. Changing preload or adding preload does not change your spring rate. Now, if you take a look at the spring rate options in the RC crawler world, there are huge jumps between the springs. Because this is mainly a crawler channel, I'm going to talk about the equipment that's specific to 10th scale RC crawlers. And they really only have 4 spring options, ultra soft through hard. Here is the advertised difference in spring rate. And as you can see, the jumps are pretty big. If you jump from soft to medium, you're almost doubling your spring rate. That's huge. In other industries, the spring rates that are available are much closer to a 10% change between them. On mountain bikes, these are the spring rates that Fox offers. 8 to 12% is about the range between the steps of the available springs. Flash back to crawler springs, and the gaps are huge. 86%, 92%. Those are giant jumps between spring rates. Now let's look at an example. Suppose you want to change your shock angle from 50 degrees to 40 degrees for whatever reason. That's going to be a 17% reduction in your spring force. Well, you can't really change springs because those jumps are huge, absolutely huge. So all you can do is conclude that changing your springs is for big changes in your spring force, and fine-tuning the angle is for smaller changes in spring force. Now, I don't love these big jumps. It'd be great to see much smaller ones, maybe have 20 or 30 springs in here, but that's not the world that's available to us. The second variable, damping force. The correct word is damping and not dampening. Dampening is what happens when you put water on something. Whatever, who cares? Damping force is very much analogous to spring force. At the 90-degree position, you're going to have a 100% response, and as you lay it down, that damping force reduces and approaches 0. Your 1-to-1 response is going to be in the 90-degree position, and as you lay your shock down, your damping force goes down, which means your wheel response is faster. This exact same chart applies for damping force. And here's the chart with the deltas. Once again, from 50 degrees to 40 degrees, you're going to get a 17% drop in your damping force as felt at the wheel. The parallel tuning method for damping rate is changing your oil weight. Here's a quick list of common RC oil weights. They range from 10 to 100. You can see there's some pretty big jumps at the beginning of the scale. 40%, 22%. Again, anything over a 10% jump, I consider pretty big. They're not super common, but if you look, you can find them. They're called half weights. They have in-between oil weights you can purchase. And these are great because then it brings down your jump between the weights closer to about 10%. Did you know if you don't have the exact oil weight you want, you can mix 2 other weights and it will equal the weight right in the middle? It's true. Now let's look at an example. Let's say you want or need to change your shock angle from 50 degrees to 40 degrees. You could have many reasons to do that. Maybe it's because you want to soften the spring rate, or maybe it's necessary for packaging on your rig. Some new component interferes and you no longer have clearance. Who cares? Whatever. Let's just say you're going to make this change. If you're happy with the shock rebound rate and you don't want that to change, you can recover that 70% drop by changing your oil weight. And if you look over here, let's say you're running a 30 weight oil, and again, you want to change from 50 degrees to 40 degrees, which is a 17% difference. If you change from a 30 weight oil up to 35 weight oil, that's an 8% plus a 7%. That's going to give you a 15% increase in oil weight. So you can effectively recover the 70% drop by bumping up 2 oil weights. See, this is why it's important to know the magnitude of the change, not just the direction of the change. If you were changing from 90 to 80, where it's only a 2% change, that's not worth changing your oil weight. But if you're down in this range, you might consider changing your oil weight to compensate. The third variable is wheel travel. Your wheel travel goes up and up as you lay your shock down. So this is actually the infinity sign, because as you lay your shock down, if your shock were completely horizontal, it would have no ability to prevent your wheel from going up and down. So as your shock lays down, your wheel travel goes up. In the 90-degree position, you start with exactly 1-to-1 travel, assuming your axle is connected at this end of the shock. Your axle will move up and down 1-to-1, the same ratio as your shock travel. As you lay it down, you get more and more travel. Again, if this is all you need to know, just a general flavor for what happens, you can skip ahead. Otherwise, we're going to go a little deeper into the weeds. Since this is mainly a crawler channel, I'm going to use a typical ultra short shock with 16 millimeters of travel. And this is the absolute change in millimeters that occurs when you lay the shock down. So again, in the 90-degree position, you've got 16 millimeters of travel. That's the exact shock stroke. As you lay it down, you can see the effective shock stroke goes up, meaning your rear wheel will travel even further. Again, it's important to note that up in the 80, 90, 70 degree range, there's not much change. But the flatter your shock gets, the bigger the jumps in wheel travel become. You can go from 16 to 30. That's almost double the travel if you went from 90 degrees to 30 degrees. So you want to be careful that you're not adding a bunch of wheel travel that you didn't want. So this might be an easier way to look at the numbers. This is the incremental delta in between each of these steps. If you're going from 90 to 30, you have to add them up. So if you're just changing from 50 to 40 degrees, that's going to be a 4 millimeter increase. If you're doing multiple steps, then you just add these together. Let's take a quick look at a short shock or a 23 millimeter stroke shock. Here are the incremental delta numbers for your reference. Again, I'll publish this document so you can refer to it later, or always come back to the video. Now, there's also a parallel tuning method for shock stroke, and that is by adding or removing internal or external spacers to limit the stroke. Here's an example. Again, let's pretend you want to move from 50 degrees to 40 degrees for whatever reason, but you don't want the additional wheel travel. So as you move your shock from this position to this position, you're going to get an additional 5 millimeters of wheel travel. So you simply want to limit your shock travel by adding a 5 millimeter spacer on the shaft. This way you're not adding unwanted wheel travel while you're tuning the other variables. The fourth variable is spring rate progression. And it's a little bit of an advanced topic that requires some explanation, so I'm going to save that for a part 2 video. In short, it means that the ending spring force is progressively more stiff than the beginning spring force. It's not a linear one-to-one relationship to the spring rate. It's a powerful tuning tool in many disciplines, but it takes some advanced understanding and a bit of explanation. The last variable is center of gravity. It only gets an honorable mention because the effect is quite small, especially on RC crawlers, but in certain disciplines, every gram counts. As you lay the shock down, your center of gravity gets lower with that shock as well. Not by changing ride height, I'm talking about simply moving the mass of the shock lower in space. Lower center of gravity is pretty much always a good thing. It's really a small effect. So what did we learn? Laying your shock down softens the spring force, quickens the damping speed because of less damping force, increases wheel travel, and it does all of these at once. So you may want to mitigate some of these impacts by changing springs, changing oil weight, or adding shaft spacers to get precisely the response you're looking for. You should also have a feel for the magnitude of the change depending on where in the angle range you're playing. Also, technically your center of gravity gets lower, but it's a very small effect. Whatever, who cares? So there you have it. If that was overwhelming, look for the much simpler intuition video version of the same concept to get you rolling quicker. If you want even more, watch the advanced tuning video that covers spring progression.